Okay, so let's get everything started up. Sorry for the couple minute late start right there. I was having some kind of an issue with my microphone, and I think it was only recording audio in one channel. I hope that didn't happen in the last video. If it did, please let me know. I'm trying to make sure it doesn't happen again if it did. Hopefully it doesn't. All right, so let's really quickly talk about um, something not directly related to the subject matter today, but instead related to the homework. I sent an announcement about this. It seems like in YO courses there is some setting in Canvas that allows you to grade assignments without making those grades visible, even though you've saved and recorded the grades. I don't think that the last time I ran a class online they had this feature. It seems like a useful feature. I did not realize that it was enabled by default. So I am sorry that you didn't get to see your grades and comments on your first 2 or 3 assignments until last night. As a apology if you didn't turn in an assignment, you can turn it in late, and since you didn't get any notifications, I will give you full points. We'll just basically kind of a do-over if you need it for those ones. Going forward though, hopefully you should be able to see your grades in there within like a day or so. I will for the most part leave fewer comments on the assignments after the first couple, mostly because I do post the full detailed keys with worked out solutions, and so if I see minor errors, I assume that you can go through and you can correct them yourself and figure that out. I will probably leave a comment if there is something, a particularly pernicious kind of difficult error that you might not catch that I notice, or if there's some just like way off base, but still good-hearted effort type of mistake. If you just write like, like the function continuous because it is, or something, I won't necessarily leave like a long comment. That's wrong, right? At this level, we don't need to write those things. We don't need to write comments like that. If it's just obviously wrong, like in a very basic way, like you didn't even try, I probably won't write some long detailed comment from now on being like, like, hey, come on, you get it. But I'll try to point out subtle mistakes, real good, teachable moments, little sign errors and stuff like that. You can check the key. It's there. It's all worked out. I type them up for a reason. And so, yeah, that'll be that going forward. Remember that these assignments are graded on a good faith effort for completion. At this level, I'm not trying to brutalize you and make sure that you can do basic math. If you're in this course, it's because you probably like math at least a little bit. So, I'm assuming this is in large ways for your own edification, and that you want to learn the stuff. So I'm not going to try to trick you and hit you with a bunch of homework. The exercises are to expand your understanding of the material, and have been selected to hopefully help give you more practice and intuition with what's going on. So I will give you good scores if you did a good faith effort. I will try to point out subtle mistakes, and I won't really waste my time on trivial mistakes or no effort attempts. And yeah, there we go. So going forward, expect to see your grades now, finally. And yeah, so I think we've got our one attendee tonight. We'll see if anyone else joins us, but everyone else will be watching later, I'm assuming, via video. So let's get back into it. Take a sip before we begin. All right, so last time we ended section 2.1, contour integrals, talking a little bit about the path independence theorem. So the path independence theorem began with a continuous function f on an open connected set G contained in C. then we got three equivalent things. The first was that the integrals are path independent. That is, if you take one path from z0 to z1, then you get the same contour integrals if you take a different path from z0 to z1. Both paths, however, must remain in this open connected set G, on which f is continuous. The second equivalent statement was that integrals around closed curves are 0. Okay, fair enough. This is kind of obvious if you think about it. You could always just go from, say, like, if you want to do a closed curve, just pick any point on the closed curve, 2 points, right? Z0 and Z1, and then just decompose them into two little pieces, right? If going on this piece, let's call that gamma naught, is the same as going on this piece, right? Then gamma, which is composed of going along gamma naught, then going along gamma 1, or I guess it should be negative gamma 1, right? Because you normally go like this, right? And so negative gamma 1 would go in the backwards direction. So here and then back there, right? So these guys, right? This will be 0 just by using the additivity and contour integrals, and the fact that if you go on the negative of a contour, then that you get negative of the integral along that contour. We did that last time. All right, fair enough. So we got integrals around closed curves are 0, and the existence of global antiderivatives for f on that region G. So kind of cool. We got antiderivatives, integrals along closed curves, and path independence all being intimately related for continuous functions on open connected sets. Cauchy's theorem, which we'll be talking about today, explores this a little bit further. In its simplest form, and Cauchy's theorem, I would like to say, is a great example of a super heavy-hitting theorem in complex analysis that is used all over the place, that is just an immediate and obvious consequence of the Cauchy-Riemann equations, these very simple relationships between the partial derivatives of the real and imaginary part of a holomorphic or analytic function. So in its simplest form, an easy form to state it, Cauchy's theorem says that if you have if gamma is a simple closed curve, where simple, I mean, it kind of intuitively just means what you think, like it's not too weird or complicated. Just think of it as non-self-intersecting except at the endpoint. That is, this is not simple while this is simple, right? So simple closed curve. So if you start and end here, right? So this is not simple because of this little part right here. Okay, so if you have a simple closed curve, and if f is analytic on and inside of gamma, then the contour integral about gamma of f is 0. Okay, does this seem kind of straightforward? Yeah. It's not that strange. All we're really kind of saying is something along the lines of the following. That is, pick some sort of a curve, right? Here's some simple closed curve, starting and ending right here, right? Let's call this guy gamma. Then we have a region inside of gamma. Let's call this like D, I don't know, right? This area in here. Yeah, let's call that, I don't know, D, right? That's the region enclosed by gamma, right? And I should be clear, understanding what being inside or outside of a curve is actually a more interesting question than it might first appear. But for the moment, we'll just take it to mean, the intuitive kind of thing that you sort of expect. We can address some intricacies that arrive later, but if you have f analytic on gamma and inside gamma, so if it's analytic on D, including where D includes this boundary formed by gamma, then if you integrate f along here, you're going to get 0. All right, so this is kind of cool. However, I would like to point out that something interesting happens if you start to, if you aren't careful, if you look at some things that we did last time and you are a little bit careless. So let's just do a quick example and let's see if we can figure out why this doesn't violate this thing we just stated. So let's let gamma be a circle of radius r centered at 0. This is 0. So for example, we could take gamma of t to be like, r e to the I t, where t is in 0 to 2 pi or something, right? So let's compute the integral about gamma of like 1 over z dz. Okay, well, if we go through and do this, this will just be the integral from 0 to 2 pi of, well, it'll be 1 over r e to the I t, and then times the derivative of r e to the I t. Okay, the derivative of e to the I t is, or r e to the I t is I r e to the I t, right? dt. Okay. Now we'll just do a little bit of cancellation here really quick. We got r e to the it, r e to the it. Oh, and hey, wouldn't you know it, what we get back after this is just the integral from 0 to 2 pi of I dt, which is just 2 pi I. Hey now, wait a second. What's going on here? Has something gone wrong? Because I know that 1 over z is analytic on gamma. It's go around the boundary of the circle. It's analytic on that, on the unit circle, on the circle of radius r. What's going on? I didn't get 0. It's because it's not analytic on the interior part, this d right here. So be careful to always remember that there is this interior region that we will end up needing, and that's what some of the interesting things about Cauchy's theorem end up being. That is, places where we don't have analyticity are in some cases detectable by integrating along a closed curve, and what this tells us ends up being interesting. So the way that we don't get 0 can matter. And as an interesting piece though to think about, however, we could do exactly the same thing now with 1 over, say, like z squared dz. Now, of course, if we do this, we're going to get, well, 2 pi, and I'm just going to book through this because everyone knows what's going to happen. This will be this r e to the I t squared times I r e to the I t dt. And so we'll just get integral from 0 to 2 pi of I over r e to the I t dt, and that's just going to be 0, right? Because we got that bad boy down there canceling each little piece out, right? We'll get I over r minus I over r, right? All right, cool. So in this case, mostly just because, remember, e to the it traces around this unit circle, so it has the same values at either endpoint. So why did we get 0? Shouldn't we get something else? 1 over z squared isn't analytic. on the disk. Okay, what's going on here? Why did we get 0? This seems like maybe it's a weird thing, right? Like, after all, like, we won't be analytic on the interior. We don't even have a well-defined value at the middle of this disk right here. The answer is because we have an antiderivative, namely 1 over z, right? Or, yeah, 1 over z. So that is a useful fact. So we have an antiderivative for 1 over z squared, right? However, for 1 over z, the antiderivative is the natural logarithm, right? And we know that that guy can be tricky. And so some things related to branch cuts will come back up again, and branches of the logarithm and what that actually means a little bit more precisely than what we've been saying so far. And what we'll find out is that, very similarly to what we were talking about last time with the existence of antiderivatives, a more general form of Cauchy's theorem will end up saying that f need not be analytic on an inside gamma, but if it has a antiderivative on an inside gamma, then this result holds. And the issue with the natural log is that we don't end up with this happening in the right way. So let's get to Cauchy's theorem itself, and or one form of it at least, our preliminary first look kind of statement of it, and let's prove it. The way we'll do this involves using Green's theorem. If anyone recalls Green's theorem from good old-fashioned vector calculus, probably did this in Calc 3, right? Green's theorem states, and I guess I should really quick say this just down here. I'll just really quick recall that Green's theorem tells us that the integral on line integral on gamma of p of xy dx plus q of xy dy, if p and q are real valued continuously differentiable functions. We're outside of the world of complex analysis for the moment. Just forget about it for a second, and just remember that from regular old Calc 3, if you're doing a line integral and you have something that looks like this, you have this nice fact which says that, hey, I can just do a double integral instead over the area enclosed by gamma of the partials. Right? So it says that integrating along the boundary, you can find it by integrating partials along the area, the interior, right? So this was, you got gamma once again, and then A is the inside of it, right? So, okay, this is just from regular old calculus. If you don't recall that one, I encourage you to go look back through your calc notes. Maybe, I don't know, go look at Wikipedia if you haven't got those handy. But it all just boils down to using the equality of mixed partial derivatives. So, partial squared f partial x partial y is equal to partial squared f partial y partial x. And that's what it all comes down to. So, all right, so let's do theorem 2.2.1. Here, we're going to suppose that f is analytic with derivative f prime continuous on and inside a simple closed curve gamma. So once again, kind of glazing over what it means to be inside a simple closed curve. Just intuitively think about what it is as the pictures you've been drawing. Then the contour integral about gamma of f is 0. Okay. So let's kind of go through this proof a little bit. So if we set f equal to u plus iv, actually let me turn down that opacity, that's a little bit intense. Then when we go through and we integrate f according to gamma, this of course is just f of z dz, and like the nice trick we wrote down before, you have u plus iv, and then you can break down dz into dx plus I dy. And then you just go through and actually multiply this out, and you just get u dx minus v dy, right? Just carry it through, u dx, then iv times I dy, that'll be minus v dy, right? And then you get the imaginary part, plus I u dy minus v dx. So these two little chunks right here are what we're going to use Green's theorem on. So Green's theorem with the, notice we got thing dx, thing dy, partial x minus partial y. Okay, we'll just do those guys right here. So u gets, like, you just flip the order, right? And then you put a minus on the middle part. So minus v partial x, since it's by that dy, and then minus u partial y, right? We put a little, so it goes right over here. Kind of think of it like that, right? Let's flip them around. Okay, and I guess maybe I should even be a little bit clearer, and I should include that minus in there, right? Okay, and then you throw on the minus in the middle, and then you do the exact same thing here. So you got v dx and u dy, and we're going to just pop these guys on down, right? And there we go. Okay, cool, good to go. And by the Cauchy-Riemann equations, notice if you go, oh, hey, you got v partial x, partial u partial y, what do these guys being 0 tell us? Well, just go on through. Partial u partial x equals partial v partial y, right? That's a fact from Cauchy-Riemann. And then over here, this would be minus partial v partial x equals partial u partial y. Hey, just straight up from the Cauchy-Riemann equations. Nothing bad at all right there. Just use Green's theorem and the Cauchy-Riemann equations. Maybe I'm making it seem like it's less, like there's less going on than there actually is, because maybe you don't recall Green's theorem, or it seems like a mysterious result. But I promise if you, it's not a complex analysis result, at least. It is something from a previous class. So I encourage you to go back and look at it. Maybe if we have time next time, we can briefly talk more about Green's theorem if people want it. But really, as long as we accept that we have Green's theorem, this is like the easiest proof in the world. It's just so straightforward. It's pretty. There's nothing to it. All right. So if we have an analytic function with a continuous derivative on and inside a simple closed curve gamma, then you get this. And as it turns out, we actually will get that f prime is continuous for free. But right now, we're going to state it just to be very clear with ourselves. And this will let us do some nice stuff. So let me pop on over to our next little chunk, which is the deformation theorem. So a little bit wordy on the screen right now, but this is just a nice kind of recap of where we're at and what we're going to do right now. I thought the textbook said it particularly well. It's like we talked about with 1 over z. It's important to be able to study functions that aren't analytic everywhere, right? You might have a curve enclosing a region, and there might be a point that the function isn't analytic there. This happens kind of a lot, particularly with things like rational functions, the polynomial equivalent of fractions, which we may care about. Okay, fair enough. So how do we, are we just out of luck? Can we not deal with them at all? What's going on? One of the things we're going to want to do when we study these guys is we'll want to be able to reduce our study to a we'll want to only study simple closed curves, and I mean simple in the just regular English vocab way, not in the fancy, like a simple curve like we just started with at the beginning of class, but intuitively just easy to deal with curves. If we have some sort of messy, like this shaped region, well, that's a nightmare. We might really want to just look at like a circle or something. After all, it's kind of like, like when we draw things, we're generally just drawing like, imagine this is like a rubber band right? It's like a rubber band, like the, it's all kind of crumpled up, but the rubber band sort of could just be a circle, right? We could maybe just kind of deform it a little bit and then have everything be okay. And as it turns out, this is what we'll be able to do. The deformation theorem is all about taking a difficult to deal with closed curve gamma and replacing it by like gamma tilde, where gamma tilde is less complicated, right? And then evaluating your contour integral about gamma tilde will be easier in some sense than if you do it about gamma. And the procedure that allows us to do this, though, comes from Cauchy's theorem. And in fact, it's just not really too bad at all. So here's kind of a preliminary version of the deformation theorem. Here, let me see if I can zoom it a tiny bit. All right, preliminary version of the deformation theorem. I'll get a little highlighter out. So we're going to let F be analytic on a region A, so on a nice open connected set, and we'll let gamma be a simple closed curve in A. Okay? And once again, remember, simple here doesn't in this case mean the intuitive English vocab word. Instead, simple in this case means non-self-intersecting. Okay, except at the start and end point, right? Because otherwise it wouldn't be closed. So we'll suppose that gamma can be continuously deformed into another simple closed curve, gamma tilde. So continuously deformed, another simple closed curve, gamma tilde, without passing outside of A. In this case, we'll say that gamma is homotopic to gamma tilde. We defined this before. Remember that a homotopy, so think of it like, we want to be able to turn, think about like having, think of it like a function, f of like, I'm going to use an x here instead of a t because we'll still normally use t's for, in our gammas. But let's just for a second consider this like this. So it'll be like, I don't want to actually go through and write everything out, but just think of it like some function f of xt, so that f of x0 is like gamma of x, and f of x1 is gamma tilde of x, right? I mean, normally we write t's right there, so sorry if that seems confusing, but the t parameter for the homotopy right here, just continuously bending it, using like a little slider that turns one into the other, right? So homotopy, we just talked about that before, but in case you've forgotten, it just means that you have a continuous function turning one curve into the other as you move from 0 to 1. You can just, it matches exactly what your intuition is. Just think of like the rubber band kind of thing, right? Like if you could sort of like poke like a rubber band sitting on a table into a nice, into that shape, then it's homotopic to a circle, right? All right, fair enough. Then what we get is that the contour integrals around homotopic simple closed curves lying in a region on which f is analytic agree. Notice right here, however, that we are not necessarily saying that, and this is really important, we are not necessarily saying that these contour integrals are 0. These guys, not necessarily 0. And that's important. That's why the deformation theorem will mean anything to us. Otherwise, this would just be immediate and obvious, just a consequence of Cauchy's theorem in the most basic way. Okay, let's go through and try to prove this. And the technique for this proof, I freaking love it. This is like one of my favorite kind of dumb tricks. I don't know why it's so satisfying to me, but the first time I saw it, I was like, oh my God, what? You're kidding. It's pretty, it's nice. So what we'll do is we'll just use Cauchy's theorem. So maybe we've got some, thing like this. We'll basically look at this. We've got some curve gamma naught drawn joining gamma to gamma tilde, right? So you've got your first curve here. This is gamma's curve. I'll try to kind of, recolor code this. Okay, and then we've got our second curve, gamma tilde. What we're going to do is we're going to just draw a straight line. It's so smooth. It's such a nice, silly little trick. We'll just draw a freaking straight line between the two of them. And the path we're going to go on is we're going to start, and I'm going to kind of put it on like a real light like highlighter right here. Right, we're going to start here, and we'll go like around all, and we go boop, boop, right back up, and we're back where we started. Whoa, cool. Or, you could go down here first, and then you could, go around, and then you can come back up and go all the way around. Either way, notice I still just have a closed curve. The only thing I'm doing is that I'm going down and back on the same path. This little gamma knot right here, when I go one way, I'll just go back the other way. And what's going to end up happening is we're going to get that part cancels out. And so the contour around here and the contour around here will get the same thing. So we first go on gamma, then gamma knot, then minus gamma tilde, then minus gamma knot. Oh, so smooth. Okay. So the inside of this curve lies in the shaded region. It's analytic on that region. So Cauchy's theorem, notice F's analytic on this region. It is not necessarily analytic in here, but because it's analytic right there, all right, fair enough. And the inside of this curve is, well, it's right in here. It's not this piece because the curve has, it goes around this part, right? Notice this will say that the integral of gamma plus gamma naught minus gamma tilde minus gamma naught. So this is going gamma naught minus gamma tilde minus gamma naught. That guy, well, I can just break it apart into each of its chunks and pull out the minuses accordingly. That is, I get the contour integral about gamma of f plus the contour integral about gamma naught of f minus the contour integral of gamma tilde of f minus the contour integral of gamma naught of f. And hey, this one and this one cancel out, and so I get that these two guys, contour integral about gamma of f minus contour integral about gamma tilde of f, this gives me 0 by Cauchy's theorem. And notice this minus right here, why are we going around this guy backwards? I hope I didn't draw that like I was going around it forwards. I think I went around it. If I did, my apologies. You go forward like this, right? Okay, you go counterclockwise, usual way. That tells you that the inside is like in here, right? All the stuff in here. Then you go this way, okay, and then you go, instead of around like this, which would say the inside's in here, we go the opposite direction, which says that the inside is out here, right? We go this way, backwards way. Oh, okay, so that's telling us that the inside of the curve is all of this junk out here, right? So that's what allows us to use Cauchy's theorem. And this is where I was saying kind of before that we're sort of glazing over what it means to be inside or outside a curve, right? When we're going this backwards way, it's going to flip what that means, right? And that's why we're going backwards in the last piece. And we'll talk about this more next time. I'm just trying to give a kind of nice high-level overview of how it's all going to work together without getting into the weeds of what some of these particular details with insides and outsides and orientations are all about. So we get 0 out of there, and because this is 0, these two guys agree, right? Okay. Now, it's important to note that we're kind of lying a little bit here, actually, and I hate that I have to tell you this because it is so much uglier to tell you it in the full detailed way, but it is important to think about. So really, strictly speaking, the new curve is not a simple closed curve. If you have been paying attention and you are watching us draw this, me draw this, and you're like, okay, so I'm going to go around this bad boy, and then I'll go down, and then I'll go backwards around that guy, and then I'll go back up. You might have been like, wait a second, when I went all the way around and then I started going down, I hit the same point I started at, and then I got down here and I went all the way around, and then I hit a point I was already at, then I went back up and I hit another point I was already at again. What the heck? That's not a simple closed curve. And it's not. So the idea that what you can do is you can actually just go, okay, well, I'll go around and then I'll stop just shy, and then I'll go down, and then I'll go backwards, or here, oops. So I shouldn't have drawn that without picking my pen up, and kind of just do like a keyhole, right? And then we make this distance here, right? Go to 0, right? So you just make that shrink down until it's like right on top of each other, and then it goes like all the way around, and then you're all good, right? See what I'm saying? Make that like that. So if you want to do the full messy thing and do that, I invite you to. We can go through what it looks like. It's just a little bit uglier. There's nothing fancy that happens. It's good to verify that that is indeed the case, and this is not fully rigorous for that reason, but it is not a informative piece of formalism relative to your understanding of the material. It's just kind of an annoying, bit of epsilonics. Anyways, we can go use this to great power when we want to deal with certain difficult issues, like certain difficult functions that are maybe fail to be analytic at a certain point, things like 1 over z, right? And what this will come down to in a lot of ways is something about topology, the topology of the domain on which a function is analytic. And this is a nice way to begin to talk about how holes end up being very important in mathematics. And what I mean here is that the kind of issues you're encountering that the deformation theorem and Cauchy's theorem, since it gives us the deformation theorem, the kind of issues you encounter are when you have analyticity on some region, but maybe not on some little hole in that region. Notice it doesn't really matter if you have, like a weird, region like this. This doesn't have any holes. It might as well be a dang circle, right? Because pick any points, and I can always take like a curve and connect them. It's path connected, but more so than that, it's I should use a different color now. It is, as we'll say, there's no way for a closed curve to get stuck in this space, right? Like I can take any closed curve and I can contract it down to a point. And that's what will motivate a definition for us. So a simply connected region is a connected region where every closed curve can be deformed into a constant curve, that is, into just a point. So think of like here's a good, nice region where if I pick a point right there and I grab myself a closed curve, I could just shrink this guy on down until smaller and smaller and smaller and smaller until I just have that point, right? I can just kind of continuously shrink it from big down to smaller, down to smaller, down to smaller. And every bit of that shrinking stays in the space. However, in example B right here, right? In this diagram right here, this curve, if I pick any point on it, doesn't matter which one I pick, no matter how I start to shrink it, notice I get stuck on this hole. Like if you imagined it like it was like a rubber band and you tried to let it go so it snaps down to that point, right? Like imagine it's like a rubber band of radius 0 and you've somehow stretched it out. If you let it go, does it get stuck on something that's not in the space? Like this little chunk right here? Think of it like it's like a peg sticking out of like a table or something. Like you got like a little like thing sticking up and like the thing's sort of just stuck on it, right? Like it can't get out of there, right? And that's sort of what's happening here. If there's a hole in your space, you can detect this by talking about how you can deform loops. That is, if you can't deform loops into points, if you can't deform a closed curve into a point, then there's some kind of a hole or a topological obstruction of some sort that's preventing you from doing that. And this can be as small as a single point, like in this final example, which we're still kind of drawing like it's not a single point. We're sort of trying to indicate that it's just one point by making the circle very small. But even a single point can stop you, right? Imagine this like a needle sticking out of a table. If you like let that rubber band snap, like it'll still get stuck on it, no matter how thin the little thing sticking out is. If there's a thing sticking out, it'll catch the rubber band. So this is the notion of being simply connected. If every closed curve is contractible, that is, is homotopic to a point, can be continuously deformed into a single point, then you have a simply connected region. And so simply connected regions allow us to rewrite a form of Cauchy's theorem. So if f is analytic on a simply connected region G and gamma is a closed curve in G, then we get the same initial result as the original, right? Okay, so we have a nice analog of Cauchy's theorem. There's nothing fancy going on here. I'm not going to re-go through a proof or anything like that at the moment. But the kind of idea of why we care about this is that it will let us deal with things like 1 over z and give us ways to evaluate integrals in terms of nicer contours. So the next little chunk right here, proposition 2.2.4, I'm looking at the time. I wonder if we'll have enough time to discuss things well. I'll just go through it right now. So the next proposition, and why we would care about doing this, tells us that if f is analytic, let me get my highlighter out, if it's analytic on a simply connected region A, then for any two curves, gamma 1 and gamma 2, any two curves joining 2 points z0 and z1 in A, we have that the integral, the contour integral about gamma 1 of f is the same as the contour integral on gamma 2 of f. And the reason we can do this, is similar to that what we did with the path integral, or the path independence theorem before. Is just that we go one way, and then you could go the opposite of gamma 2 back, and via this nice Cauchy's theorem for simply connected regions, we get that we have path independence again. All right, so let's compare this really quick, because maybe it feels like we're just sort of covering the same ground again. So here we have that f is analytic on a simply connected region A, right? That's the only thing we need. F is analytic on a simply connected region A. So I'm going to go back to the very beginning of what we were looking at, the path independence theorem. Here we had f continuous on an open connected set G. Then we got path independence is equivalent to integrals around closed curves are 0. That feels like what we just were looking at. And the big thing is this antiderivative right here. There exists an antiderivative, a global antiderivative, right? Okay. Now, this will end up being quite important for reasons that I don't think that we'll have enough time to adequately talk about today, but we will talk about next time. But notice, this is not the same initial assumptions. Here we just have a continuous function on an open connected set. What we have in, in this situation is an analytic function on a simply connected region. And this is basically what we're doing now is we're building things out into the analytic case, and this will give us a lot of things for free. What those things are, we'll discuss next time. Today, we just basically went through our first look at Cauchy's theorem, and next time we'll talk about how um, the failure of 1 over z, integrating that about the unit circle, gave us like 2 pi I, right? The failure of it to be 0 is in some sense related to, uh, or is not in some sense, in a very specific and very clear sense that we will precisely describe, um, is caused by um, the non-uniqueness of, or the non-uniqueness of the logarithm, its antiderivative, and our inability to define it on an appropriate region. So we'll bring this back up, and this will give us a more nuanced version of what it means to be a branch of the logarithm, and it will really shed a lot of light on things. So we'll leave it right here for today, and we'll pick it up next time. If you have any questions, please shoot me an email, and if not, cool. Have a great night.